Okay, so hello everyone. This is my name is Ryan and from Construct University, and I'm going to be presenting a presentation that we did at ICNC 2025. And this presentation is going to be titled Joint Channel Estimation and Data Detection for AFDM Receivers with Oversampling. I would like to also take a moment to appreciate my colleagues. So there's me and then Professor Abru from Construct University as well, and also our colleagues from NTU, Yao Ge and Professor Guan. So this work was done in collaboration with NTU as well. And let's dive straight in. So this is a small slide with the content of the overall presentation. So we have a gentle introduction to the topic, and then we describe the generalized oversampled time domain relationship for arbitrary signals. And then we describe the oversampled AFDM relationship for these signals. Then we describe the mechanism for the joint channel estimation and data detection procedure. And finally, we do a performance evaluation to see how the performance fares against conventional receivers. So, as the wireless community is probably aware of, there has been a recent candidate for high mobility wireless systems called the AFDM modulation scheme. So this is actually a very promising candidate for 6G communications, for example, and is up there with, for example, OTFS. So that is to say orthogonal time frequency and space modulation, and also the conventional OFDM systems that we have. So what's nice about AFDM is that unlike OFDM, it doesn't suffer as much when there's high Doppler shifts in the environment. And from the perspective of OTFS schemes, as you probably know, OTFS is a two-dimensional modulation scheme and therefore has a higher modulation complexity than typical OFDM systems. So these AFDM waveforms avoid that completely, as in to say they have the desirable properties of the robustness to Doppler shifts and also the full diversity conditions in doubly dispersive / high mobility channels, while also maintaining the low complexity of OFDM waveforms. So in this presentation, we are going to describe a joint channel estimation and data detection procedure for oversampled AFDM signals. And by oversampling in this sense, I mean that while typical systems sample the time domain received signal at a Nyquist rate to avoid aliasing, we go one step further and oversample these signals and see if there's a gain. So starting off with the time domain relationship, consider a typical point-to-point SISO AFDM system where you have just a single antenna transmitter and a single antenna receiver in a high mobility environment. That is to say, we have a doubly dispersive channel that can describe the environment as given in equation 1. So as you can see here, this is a general time delay channel with a distinct number of P paths. And this HP is going to be the complex channel coefficient. And the Doppler shift is going to be presented as nu P, given in green over here. And the delay in per path is going to be given by tau P. So as you can see, this model now encapsulates all of the information of the scatterers and surrounding, given Doppler shift and delay to each of them. So correspondingly, we now have a time domain received signal given as in equation 2, where you can see is just a typical convolution between the time delay channel and an arbitrary transmit signal, time domain transmit signal. And the convolution can be expressed as seen here, where as you can see, the nice time domain relationship still persists, and we take an integral over the delay dimension. So we can now do the oversampling procedure for equation 2, and we end up with equation 3. So what's also nice to note here is that we do this, we define a sampling rate, Fs, which is to say we take the typical Nyquist sampling frequency, which is usually set to the bandwidth in typical OTFS and AFDM systems, and we multiply it by some oversampling factor. So this G is the oversampling factor, and is usually an integer number. So for example, it can be, if it's 1, then we fall back to the typical Nyquist sampling rate. If it's 2, we are oversampling it by 2 times. So we are getting 2 samples per symbol transmitted. When G is 3, we get 3, and so on. Right? And then we plug this into our equation that we had before, and we get the relationship as given in equation 3. So as you can see, now the channel actually changes a bit. Previously, it was just n here. Now it's actually, there's a small addition in the exponential here, where it's now n plus g over big G. And this small g is just the sampling index. So for example, if the big G is 2, then our small g will be 0 and 1, and so on. So it's just a sampling index of the oversampling rate that we have. So this can now be expressed as in equation 4, where we describe the G sample stream as a sum, as a discrete sum from L equals 0 to infinity. So as you can see, now we define a discrete Doppler shift, a digital Doppler shift, so to say, where we have now this FP, which is usually defined as a factor of sampling frequency, and also an LP, which is now the discretized version of the original delay tau p that we had before. Yeah, so now we can use the typical cyclic prefix definition and rewrite equation 4 in this nice vector form, as in equation 6, where we have the G sampling stream described as so. This part highlighted in red is going to be our channel, effective channel, so to say, in the time domain. As you can see, all the previous characteristics that are described persist here as well. We have the complex channel gain. We have the psi p, which describes the cyclic prefix for an arbitrary waveform. So this is going to be different for each of the waveforms that I'm going to describe that can be used. And it has a typical definition for AFDM as well. So this omega here is going to be describing the relationship between what happens to the matrix when you have a Doppler shift. As you can see, it's a function of this FP here. This omega, by the way, is the diagonal matrix. I can just show it here. It's going to be a diagonal matrix scaled by the factor G over n times big G. And this pi is what happens to the channel when there's a delay involved. So as you can see, this pi is a cyclic shifted matrix. And now we can take all of this and define a general psi of G, and we have a input-output relationship in the time domain for arbitrary oversampled signals. So we have to first, before we go to the AFDM case, also discuss what's going to happen when we oversample at the receiver, right? Because the AWGN noise that is almost always present in communication systems is going to have some correlation, since we are going to be sampling each symbol multiple times. So we can now define a model for that too. And to do that, we first define this C of W, which is the Toeplitz matrix constructed as in equation 10. As you can see, this CW, it depends on small g and big G, which are the oversampling factors. And it's a function of the signal to noise ratio, of course, and also the pulse shaping that we could use at the receiver. So for example, in a typical raised cosine filter, you're going to have this type of function, which is going to be a function of G and G. And you could also have a sinc function and so on. The choice of the pulse shaping is arbitrary at the receiver. So now we can do a Cholesky decomposition of the CW, yielding this matrix LC, right? And then we can take some uncorrelated noise vectors as defined here. This W of UC denotes the uncorrelated noise vectors. And to get our correlated noise samples per G stream, we can just multiply this W of UC with this LC, and all the vectors that we're going to get here are going to be correlated noise samples. So this is going to be the model for the model to deal with the noise correlation in the model. So now we can go start describing the AFDM modulation scheme. So as you can see, in the previous step, we described arbitrary time domain signals, right? But here, now we're going to focus on AFDM. And as you can see, AFDM modulation can be described in a single step. So this X is just symbols picked from an arbitrary constellation. For example, consider QOM or QPSK, 16 QOM, and so on. Any of those goes. You can just pick symbols from a discrete constellations and form this X, which is an n/1 vector. And to do the modulation for AFDM, you just have to multiply that X with this matrix that's defined here. So it's, as you can see, it's somehow like a OFDM, because if you just ignore the lambda matrices, it's just Fn Hermitian times X. Fn Hermitian here, by the way, is a normalized DFT matrix, which is typically used in OFDM communications. And what makes this AFDM is now the Fn is actually sandwiched between these lambda matrices. And these lambdas are two diagonal matrices parameterized by this C, right? So this C controls these are called frequency parameters, which control the slope of the AFDM modulation scheme. And these parameters actually can be tuned to give AFDM this robustness against high Doppler shifts in doubly dispersive channels. So this is the AFDM modulation step. And as you can see, once we have this, we can now write the received signal down as in equation 14, which is all we're saying here is that we have our R in time domain is going to be this psi of G that we described before with all the features as it is, multiplied by this SAFDM and the correlated noise samples, of course. So we can now demodulate to get the final input-output relationship. As you can see, the demodulation is also pretty straightforward. We just take the Hermitian of this, as in modulation. The modulation is the Hermitian, and then the normal demodulation step is going to be as before. The proper this is called the discrete affine Fourier transform. More details on the on the paper, but as you can see, it's just now the channel that we had before is sandwiched between these two operations, and we can now get the final input-output relationship as in equation 16, where we define a GAFDM, which is going to be an effective channel in the discrete affine Fourier domain. So the structure of this G is also pretty similar to the previous one that we had before, where we have this channel matrix. As we see, this is upside, right? And it's encapsulated within these modified Fourier relationships where you have these lambdas on both sides and the DFT matrices, of course. So now let us first define a gamma. So our gamma was this part over here. So we can write GAFDM is a sum on P, HP times the gamma of P. And now we can go on to design our receiver structure. So what we can do is we can now put all of this together and stack them up. And now we have for each oversampled stream. So now we have y is 0 to g-1, and then we have a bunch of gammas, as you see, and all the correlated noise samples. So now this effective received signal y is going to be a gn/1 vector instead of nn/1 vector. Of course, when g is equal to 1, there's no oversampling, and this falls back to the normal n/1 vector that we have in typical systems. So we can now write this equation 18 element-wise as given in equation 19, where we're just saying that the nth y, so the nth symbol, nth received signal, can be written as this double sum, as you see here, where this HP is now the complex channel gain. This gamma contains all the delays and Doppler shifts, and this XM are the symbols to be estimated. So in this procedure, the goal is to jointly estimate both of these XMs, all of the XMs for all M, and HP for P, given knowledge of YN and gamma P. So we can now start describing a JCEDD procedure. So it's joint channel estimation and data detection. So first we define a typical MSC for both the data symbols and the channel estimates. As you can see, it's pretty similar to how the mean squared array is defined here. Oh, and one more important thing to note is that we now have to devise message passing rules, and we have to do a parametric bilinear message belief propagation algorithm to deal with the fact that we have to estimate both the X's and the H's. So the first step of this would be the soft interference cancellation. And we can do the soft interference cancellation as follows. As you can see in equation 21, we have the soft interference cancellation for our data symbols, this y tilde of x's for all m and n. And we just subtract all the necessary components, and the goal is to approximate these terms as interference plus noise, right? So we can also calculate the corresponding variances by writing it as in equation 22. And the full final conditional variances for the data is given in equation 24. So it is a bit of a mouthful, but as you can see here, what really matters is that these soft interference cancelled variances, these conditional variances, are actually dependent on the estimates of the data and the channel estimates, right? So, and there are some mixed terms in here as well. And one more nice thing to note is that while but the reason that this is an approximation is because we don't have instantaneous values of the mean squared error of the channel and of the channel estimates and the data symbols. So we have to replace them with long-term characteristics. As you can see, this is what we do here. This ES is a long-term MSC of the data symbols, and these H hats, these are going to be like the instantaneous, but also they come from what the long-term characteristics of the channel estimates too. So the procedure for the soft interference cancellation of the channel estimates is also very similar. I will skip through the steps here so that I can show the final expressions for the SIC and the corresponding conditional variance. As you can see, the terms look very similar. There are some minor differences, of course, since this is a parametric bilinear problem, but the general idea still holds here. So the next step would be the belief generation stage. So we now have to calculate, leveraging those previous soft interference cancellation symbols and the variances. We now have to calculate some extrinsic mean and variance based on those. So we now use scalar Gaussian approximation for this. And we can write our conditional PDFs as given in equation 29 with the corresponding means and variances given in equation 31. So these are very similar to the typical linear belief propagation as well. And we just make use of the fact that we can approximate all of the SIC as Gaussian noise, and we can compute the extrinsic means and variances that way. So similarly, we can do the same job for the channel estimates too, where now these are the means and extrinsic means and variances. So the final step of the belief propagation is a step that we call denoising. So in this stage, we are going to use all the information that we have calculated previously. So our extrinsics to get like a soft replica of the symbols that we're trying to estimate, right? Of symbols and channel estimates. So for the data symbols, since we know that they come from a discrete constellation, we can, without loss of generality, choose a QPSK denoiser, for example, if we are using QPSK symbols. And the QPSK denoiser is given as in equation 35. As you can see, it's the soft replicas are going to be a function of the power. The Cx is just a scaled power of the symbols themselves, which is assumed to be known, and of course our extrinsic means and variances that we calculated before. So we can also use the belief damping procedure here to avoid unnecessary and wrong estimation convergences to local minima instead of a global minima we are searching for. And similarly, for the channel estimation as well, we can apply the Gaussian denoiser to get the soft replicas for the channel and its corresponding variance. So these are some of the performance evaluations for the bit error rate. As you can see, the black lines are what happens when you have a typical system without any oversampling. And as you can see, this black ball is going to be when we have the typical Nyquist sampling rate, and when we have 32 pilots in a system with 128 subcarriers. And as you can see, what we really gain here is that when we use a lower number of lower number of pilots in this situation, sorry, in a normal system, the performance degrades quite a lot. But now looking at the oversampled system, as you can see, this red dot with the red color marker is going to be like this. But even when we have 4 pilots, it still performs really well, right? And it's going to be a similar case for the NMSC performance of the channel estimates too. As you can see, we have a significant gain over typical Nyquist sampling rate frequencies, and it really shows like the gain when you have a lower number of pilots, and the oversampling compensates for that. Yeah, so that was about it. Do you have any questions?
Yeah, I have one. So
Yeah.
in your scheme, your frame structure uses some NP pilots, followed by the data symbols, of course. So
Yes.
is there an optimal way or optimal pilot design or even placement in the context of this oversampling strategy to maximize the performance gains? I am asking you this because obviously the pilot configuration impacts your JCEDD scheme. So I was thinking if you already considered or no.
Well, so to directly address, there is probably an optimal pilot structure that we can use, but we did not look into that quite yet, because for AFDM signals in particular, what we do is we usually have some pilots, as usually done in OFDM, and then we have the data, right? But also AFDM has been used in ISAC scenarios, and in these ISAC scenarios, there have been studies done with frame structures with just 1 pilot and a guard interval. So that type of frame is optimal for ISAC. So I think from what I can say, there is probably an optimal frame structure for these oversampled systems, and we can probably optimize that too. But that's more of a resource allocation problem, I would say, to optimize the frame structure for this oversampling situation. Yeah, does that help?
Yes, thank you.
Okay.
I also have a question. So
Yeah.
the channel model that you use here is a doubly dispersive channel model, right?
Yes.
But the oversampling that you were doing is only in the time domain, if I understood
Yes.
correctly. But
Exactly.
couldn't this also be done in the frequency domain? So you have
Well,
like an, yeah, that would be
sorry.
my question.
So yes, well, in a sense, I think I'm not exactly sure. There have, of course, been studies done on OFDM signals that have been oversampled in time domain and frequency domain. And I think
Mhm.
there were some differences in the performance. But in this context, I'm not exactly sure where the gain would come from if you do this procedure in the corresponding domain. For example, this is done in the time domain. Yes, but even if you look at the the DAF domain representation of AFDM, as you can see here, there is probably not going to be much of a difference.
Okay, so you believe that you are already extracting most of the gain due to oversampling if you do it already just in the time domain. And
Yeah,
you
because
don't
the
believe
transforms
that.
are linear, right? Yeah.
Okay, makes sense. All right, thank you. That's all from my side. That was very interesting.
Yeah, great.
Okay, so thank you very much, everybody, for watching. And I think we can stop here.